Hello friends. So today we are going to discuss four questions, and these four questions are from the year 2007, 2008, 2009, and last one is 2010. So they are total of four questions. So the first one, which was asked in the year 2007, and it is given as a magnetic field B naught J unit vector exists in the region A, region X which is greater than A but less than 2A, and there is the magnetic field B which exists in which is given as minus B naught J in the region X greater than 2A but less than 3A, where B naught is a positive constant. A positive point charge moving with the velocity V naught I, it should be I unit vector, where V naught is a positive constant, enters the magnetic field at x equal to A. The trajectory of the charge in this region can be like. So in this case, we have a point charge, and the point charge is moving with the magnetic field which is given as from 0 to A, it is 0, and then from A to 2A, it is having a positive. So here we have B naught J, and from 2A to 3A, it is having a minus B naught J. Therefore, we have to find out what will be the trajectory of the charge that is moving in this magnetic field. And one thing for sure, we know that whenever there is a charge moving in the magnetic field, it traces a curve or trajectory which is a circle, and that circle can be a quarter circle, can be half circle, can be 3/4 of circle, or can be a 1/4 of circle, but it will be somewhat related to the circle itself. So first of all, let's find out the force for both the region. So we can say direction of force when x is greater than A but less than 2A. So in this condition, we can write our magnetic force Fp will be equal to Q, and we have here V cross B, and we substitute the respective equations. We get this as Q, and we have V naught I cross B naught J, and this gives us that the magnetic force will be equal to Q V naught B naught and K unit vector. So it means the direction, it is along positive Z direction, positive Z direction, and charge will move in a circle in XZ plane. Charge will move in a circle in XZ plane. So we can just draw a approximate figure for that. So this is our x-axis and this is our z, and the magnetic field start from point A. So it will try to, we can say, make a circle, and that will be something like this. And now we come to the, or we can also find out the radius. Let me write our radius. So we can say the radius r will be equal to m v naught divided by q times b naught. Now we come to the force for the second region, that we have determining force for x greater than 2a but less than 3a. So we can write that force, for the sake of convenience, let us call this as 1 and this as 2. So we can write this as q. Once again it will be our v naught I cross minus b naught j, and this gives us q, and we have here v naught b naught k unit vector, and its direction will be along the negative z direction. Negative z direction. But the plane will be still our xz plane, but in opposite direction as that of first region. So you can say the charge will move in a circle in xz plane, but in opposite direction as in first region. So here also we can find out a radius. Radius will be same. Radius will be our m v naught divided by q times b naught. Okay. So radius in the both the cases will be same, because the magnetic field as such there is no effect on the velocity of the charge because of the magnetic field, because work done is 0. So we can draw the approximate for this also. So we have this as x, this is z, and it is suppose somewhere here it is 2a, and now the charge is already at 2a. So this is our 2a, and now it will traveling in opposite direction, so it will be coming something like this, and this will be continue up till 3a. So if you combine these two figures, we can draw an approximate figure for that. We have our x and we have a z. So from it start from a, and from a it takes a circular path like this, so it will be taking circular path like this, and up till 2a, and after 2a it is going to follow the circular path in the reverse direction. So this will be like this, okay. And this will be up till our 3a, and if we complete the circle will be something like this. So this will be the radius of the circle, and on the other side it will be something like this. We're not very sure how it is going to behave, so we can just make an approximate that. You can just let me, because the radius is same in both the cases, so therefore our 3a will be somewhere here, and this will be our radius. So therefore the actual, you can say, shape of the graph will be something like a S curve. Okay, so you can say the actual shape will be something like a S curve, like this. So at least you can say in that option number A is the closest representative of that. So we get the option A is the correct one. Option A is correct. Next question. It is given that it is asked in the year 2008, and it says that a particle of mass m, charge q, moving with a velocity v, enter region 2 normal to the boundary as shown in the figure. Region 2 has a uniform magnetic field B perpendicular to the plane of the paper. The length of the region 2 is L. Choose the correct choice or choices. So this is a multiple correct, and we have to find out that which of the option is the correct one option here. So in first case it says that in the first option, enter region 3 only if the velocity is greater than QLB by m. Enter region 3 only if the velocity is less than the same quantity. The path length of the particle in region 2 is maximum when the velocity is equal to this one, and the time spent in region 2 is same for any velocity v as long the particle returns to region 1. So we have three regions: region 1, region 2, region 3. Region 1 has a magnetic field, and the direction of the magnetic field is into the plane. And we have a, you can say, particle which is traveling. Let us suppose we can just draw the axis. So let us suppose this is a x-axis and we have a y-axis. So it is traveling along x-axis and perpendicular to the magnetic field. So entirely, because the charge or motion of the charge will be only affected by the magnetic field, so we are mainly interested in only region 2, whose length is given as L. So we start with motion in region 2. Motion in region 2, and we have that our velocity is perpendicular to the magnetic field. So therefore the particle moves in circular path. The particle moves in a circular path and we can find out the force. So our force will be equal to Q V cross B. Because of the 90 degree, we can write this as QVB, and this will be providing our required centripetal force. So we can say this is equal to mv square upon r. So from here we can say the radius will be equal to mv upon qb. So this is the radius. Now we find out, or we can say we can make a comparison between the radius of the circular path and the length of the second region. Or indirectly, we are going to find out the condition for entering region 3 by making the comparison between R and L. So we say condition for entering region 3. So we are given that the length of region 2 is L. Length of region 2 is given as L. Therefore, we can say the particle to cross into region 3 we can say that you can say that the particle should move far enough so that at least it crosses the distance r. You can say the particle should at least cross the length L. Okay. And we already know that the particle is moving in the circular path for radius r. So therefore, you can say for circular path to reach region 3, radius of the circular path should be greater than length L. So we substitute equation for radius, we get this as mv divided by qb is greater than L. This gives us the velocity should be greater than qbl upon m. So it means option number A is correct one. Option A is correct. Now we have to find out the maximum path length. Maximum path length, and we know that our velocity is our qbl upon m, and we can say the maximum path length, that is our r, should be equal to L. So under this condition, the particle just grazes the opposite boundary and turn back. Okay. When the radius is equal to the length, that the length of the region 2. So under this condition, the particle just grazes the opposite boundary and turns back. So therefore, this is the maximum path length possible in region 2. Possible in region 2, and we can draw an approximate figure for that also. So this is our region 2, and if the particle makes a semicircular path like this and the radius is just equal to the length, so it will be moving in this direction. So this is our length, and suppose this is the center of the circle and this is our radius. So if radius is just equal to the length, then it is going to just graze the region 2 boundary wall on the right side and turn back and come back to the, so option number C is the correct one. Option C is correct. Now we find out the time spent in region 2. In region 2, and time spent in region 2 means it is going to return into region 1 back. It will not cross into the region 3. We can say that particle returns back to region 1 and does not enter region 3. So it means it completes semicircular path or half circle. It completes semicircular path, or we can say it is a half circle. And time period for circular motion, we already know the formula. Time period of circular motion, that is our capital T, will be equal to 2 pi by omega, and we can write this as 2 pi by m divided by q multiplied by b. We need to find out only for the half circle because that is the only portion it is moving in the region 2. So therefore we can say time for half circle small t will be capital T divided by 2, and this gives us 2 pi m divided by 2 qm. 2 goes with 2, and we get this as small t is equal to pi m divided by, sorry, it has to be qb. And in this particular equation we can see that there is no velocity in this equation, time equation. We can say this does not depend upon v, does not depend on v. Therefore we can say option number D is also correct. Option D is correct. think one option is left. Yeah, option B is incorrect. Okay, because it is just opposite to option number A. If A is correct, then B has to be false. Next question, which was asked in the year 2009, and it states that a steady current I goes through a wire loop PQR having a shape of right angle triangle with PQ 3x, PR 4x and QR 5x. If the magnitude of the magnetic field at P due to this loop is K times I mu naught pi 48x, find the value of K. In this case, we are having a, you can say, a triangle, and that triangle is in the form of a right angle triangle, and that is right angled at P. So we can just draw an approximate diagram for that. So this is a P, Q, R, and we are given that QR is 5x. Okay, 1 second, I think QR, let me correct it, QR has to be hypotenuse because that's the longest one. So we have Q, R, and this is P. So length of QR is given as 5x, length of PR is given as 4x, and length of PQ is given as 3x. We have to find out the magnetic field at P due to the loop. So we have to find out the magnetic field at this point P. So basically, and the current is flowing from in the loop. Okay. And it is given, or we can say that independently we can consider this as a 3 independent wires. One wire is our PQ, another wire is our PR, and the last wire is our QR. And based on this, we are going to find out the magnetic field at point P. So from the figure, we can easily understand that point P lies on the wires, that is QP as well as PR. So we can say that for sides PQ and PR, point P is at one end of the wire, is at one end of the wire. Okay. Therefore, we can say the magnetic field at this point will be equal to 0. Therefore, magnetic field will be 0. It means magnetic field due to wire PQ and magnetic field due to wire PR will be equal to 0. And the third wire, that is our QR, will be only the contributing towards the magnetic field at point P. So we can say that side QR will contribute to the magnetic field at P. Therefore, we can just draw an approximate diagram for that. So this is our Q and this is our R, and our point P is somewhere here. And let us draw a perpendicular distance between this. So this is our point P. And we can just join these two lines. And this, let us suppose, is our phi 1 and this angle is phi 2. Okay. So we can write that the magnetic field due to QR, according to Biot-Savart's law, magnetic field at P due to QR, and we can write this as B is equal to mu naught I upon 4 pi integral dl cross r unit vector divided by our r square. And this can be further solved as, you can write, for a finite wire, the magnitude of the field at a perpendicular distance d, and that is given as B is equal to mu naught I 4 pi d, and here we have sine of phi 1 plus sine of phi 2, and this is perpendicular distance d. So let us find out perpendicular distance. The perpendicular distance d, and we know that area of triangle A is our half our PQ PR, which is half 3x 4x. So area will be coming as 6x square, and we can express the same area in terms of the height as well as the hypotenuse QR, because area is also half base into height, and area is equal to half into QR multiplied the perpendicular distance, that is D. So this gives us a 6x square is equal to 1 by 5 1 by 2, and we have 5x multiplied by D. So this gives us that our perpendicular distance D will be equal to 12x and divided by 5. Next, we are going to find out the angle, because we know we want sine of phi 1 and sine of phi 2. So it is a right angle triangle. So we can write sine of phi 1 will be equal to 4 by 5 and sine of phi 2 is equal to 3 by 5. And we require their addition. So we can say sine of phi 1 plus sine of phi 2 is equal to 4 by 5 plus 3 by 5, giving us 7 by 5. So we know all the relative things. So therefore, we can write magnetic field because of QR will be equal to mu naught I. We have 4 pi. Distance we found out is 12x upon 5 multiplied by 7 by 5. And this gives us 5 cancel with 5. So we are left with this as 7 mu naught I upon, this comes as 48 pi x, and the given formation is K mu naught I upon 45 pi x, and from this we can clearly see that this gives us the value of K is equal to 7. We come to the next question. It was asked in the year 2010, and it states that we have a thin flexible wire of length L is connected to two adjacent fixed points and carries a current I in the clockwise direction as shown in figure. When the system is put in a uniform magnetic field, strength B, going into the plane of the paper, the wires take a shape of a circle. The tension in the wire is. So this is, you can say, so this entire is divided into two parts. So in the first part, we have wire and the current is flowing in clockwise direction. Let us suppose that the current is I. And when this is put in the magnetic field is down the plane, this wire take place in a shape of a circular, and we have to find out the tension in the wire. So in this case, because of the magnetic field, as we put the wire in the magnetic field, there will be force acting on the wire which actually makes it in the form of the circle. So let us consider a small portion of this wire, and that small portion of the wire, let us draw it like this, and we have a center of this circle because this is a part of circle, and let us join it here, and this each end of this small section is making an angle of theta by 2 with the vertical, and the tension in the wire will be along as it form of tangent. Okay, so if we draw the tangent at this place, so we are going to have tension in this direction and another tension in other end of the wire. Now this tension can be divided into two components, and vertical as well as horizontal. So we are going to have this, it will be our theta by 2. So we can write this as cos t cos of theta by 2, and this will be our t sine theta by 2. Similarly, it will be up to the other end also. So we are going to have this as theta by 2, this giving us t cos of theta by 2 and t sine of theta by 2. And in the, you can say, you can say in upward direction, because of this magnetic field, we can say there will be some kind of magnetic tension that will be acting in this portion of the wire, and that will be in the outward direction. So let us call that FB. Okay. So as entire thing is in balance, and we consider that this is a small segment, and this small segment is of the length ds, and r is the radius of this small particular segment. So we are given that the length of the wire is L. So we are given that length of wire is given as L, and this wire forms a circle. Forms a circle of radius, let us suppose that is our capital R. Therefore, we can write that our length will be equal to 2 pi r, and from here we can write that our radius is equal to L upon 2 pi. Now we analyze the force on the wire. Force on the wire. So in the uniform magnetic field, the current carrying loop experiences a zero net force, but there is a magnetic tension. So you can say that in a uniform magnetic field, a current carrying loop experiences a net zero force, but there is a magnetic tension in the wire. And so we are going to find out what will be this magnetic tension. For this, we consider a small segment of wire. So we get ds is equal to r d of theta, and the force on this segment, force on this segment that is our df is equal to I ds cross b. We substitute value of ds, we get this as I r d theta b sine of 90, and this gives us that the force df is equal to I b r and d of theta, and this will be acting radially outward, acting radially outward. Now we can find out the balance of the force. Balance the forces. So as the wire is in equilibrium, so the outward magnetic force is balanced by the tension in the wire, which acts tangentially, as we have already seen it. We say the wire is in equilibrium, so outward magnetic force is balanced by tension T, which acts tangentially. So once again, for the small segment d theta, for small segment, we can write, because there are two inward component, okay, from the both side, you can see that there is this t sine of theta by 2, and another one is also t sine by theta by 2. So in the downward direction, there is a contribution of both these components. Now the angle we have taken is small angle, that is d theta. So we can modify it. We can write that 2t sine of d theta by 2, and we can approximate for the small angle, we can write this as 2t, and we have d theta by 2, which gives us as t d theta, because here 2 goes with 2. So now, as it is balanced, therefore the outward force, let us call this outward force not Fp but Ft. So we can say that outward magnetic force is equal to inward tension. Therefore we can say that our I br d theta will be equal to T d theta, and this gives us that the tension T will be equal to I b r. So this is the tension in the wire, and we can also substitute the value of the radius. So we can write that tension T will be equal to I b L upon 2 pi. So this is the tension in the wire. Yeah, so these were the all questions. There were 4 questions, each from 2007, 2008, 2009 and 2010. So this complete all the 4 questions. Thank you.